Today we're going to learn about ionic radius. This is important because one of the two types of bonds we're learning about is ionic and the other one's covalent. But in ionic bonds, what is bonding is the ions, specifically the positive ion, the cation, and the negative ion, the anion. When ionic bonds are formed, they're very different from covalent bonds. There is not a discrete particle. If you notice in this diagram here, there's a lithium and a fluoride, but every single lithium is bonded to multiple fluorides all around it, and the same for every fluoride. So when an ionic bond is broken, you're breaking more than just one lithium fluoride away from another. You're breaking lithiums away from multiple fluorides and fluorides away from multiple lithiums. So it's a much stronger bond. Now, other trends we've learned about in this unit that have been important have been electronegativity. Remember, electronegativity applies only when you're talking about shared electrons in a bond. Remember, the most electronegative element is fluorine, oxygen is number 2, and then nitrogen is number 3. Another important trend we've talked about is atomic radius. Atomic radius is just how big is the atom. Remember, atoms get bigger as you go down a family. And the reason they get bigger as you go down a family, you're adding another orbital. First we have 1s and we have 2s, so every time we add another orbital, the atom gets larger. Remember, the atom gets larger as you go to the right, because as you go to the right, the nuclear charge or the number of protons increases. Now true, we're adding electrons, but those are not shielding electrons, and so those protons are able to pull the atom in much closer. So that leads us up to our new trend, which is ionic radius. Ionic radius follows the same exact trend as atomic radius. Atoms get smaller as you go to the right, and they generally get larger as you go down a family. But there's a little bit of variation. So let's look at some differences in this and some within these. And one thing we want to do is compare one ion to a neutral ion of the same atom. So, for example, we look at this ionic radius. Notice that generally we see the atoms get bigger as you go down, but the trend is only true within the metals versus the nonmetals. Notice the metals for the atomic radius ionic radius get bigger as you go to the right, but then we restart the trend again when we have with the nonmetals, because notice the nonmetals are not comparable, and the nonmetals specifically are a different color here. So you see the ions are a little bit larger, and they're, I guess, a reddish color. And so notice that the same trend is not true for these because there's a different number of electrons. So for this, the trend is true for the metals, but for the nonmetals, that same trend does not hold true. So ionic radius. So one thing we're going to do mainly with ionic radius is consider the neutral atom to the ion. So what you see here is, for example, we have lithium. The lithium atom, or lithium 1+, is much smaller. And this is true for, notice everything on the left here these are all the metals. So all the metals which are on the left, the positive radius is much smaller than the neutral radius. Then over here on the right hand side we have the nonmetals. For the nonmetals, notice the negative ion is much larger than the positive one. Why is this? Well, and we can also see if we look at the ionic radius of, for example, these are out of your text. If you look at lithium versus lithium ion, sodium versus sodium ion, potassium versus potassium ion. In each one of these cases, the cation is smaller. Then when you go to the nonmetals, the anion, the negative ion, is larger. Why is that? Well, if we look at each one specifically, actually it's pretty easy to determine that. So a couple of factors we want to look at, really 3 specifically. One is electron configuration, the other is a number of protons, the other is a number of electrons. Notice the only difference between the electron configuration of sodium versus sodium ion is this 3s1. In this sodium ion, 3s1 is written here, but this would actually be deleted. There is not a 3s1 in sodium because it has one less electron. So the entire electron configuration is 1s2, 2s2, 1s2, 2s2, 2p6. So one reason sodium is much smaller, the sodium ion is much smaller, is it's lost this entire orbital. So remember, when you're doing an electron configuration, the numbers denote an orbital that's further away from the nucleus. So we've lost a 3s, which is much further away from the nucleus. So that means a sodium ion, it's much smaller because the 3s doesn't exist. Also notice the number of protons is the same, but the number of electrons is one less. So you have the same number of protons pulling in even fewer electrons, and you lost an orbital. So cationic radius, the cation is always smaller than the neutral metal. Now let's look at anionic radius. Now the opposite is true in an ionic radius. So what we're going to do is look at the electron configuration, the number of protons, and the number of electrons. So when we do that, notice the same thing here. For chlorine, we have, this is the what we call the electron configuration, but this is the ground state electron configuration for both of these. And then notice the difference here with the chlorine ion is we've added one more electron, specifically in a 3p level. Now it's got a full outer level. But what happens here is we have the same number of protons, but in the anion we actually have more electrons. So we have the same number of protons pulling in more electrons, which gives you a bigger atom. So for the anion, the ionic radius will always be bigger than the neutral atom. I think that's pretty